already. The creature says good morning, apparently. Or he's mad that there's a car outside, or who knows. Anyways, let's kind of start off with our schedule for the rest of the semester here. So we are going to have, I suppose, starting today, probably through, I would say the 26th, probably. Maybe a little longer. Let's say the 27th, because this is an annoying chapter. We'll talk about transition metals, which is chapter 23. After that, we will have probably... We'll see what we do. Maybe on the 28th, we'll just take the day off. We'll see. Or maybe we'll start nuclear. Why not? And that's a shorter chapter, so we'll probably finish it by... we'll probably only need 2 or 3 days on that. What we can do on the 5th and 6th, we'll spend those days reviewing. And then the week after, on the Monday and Tuesday, so you'll have a larger window of time, you will take your final exam. A few notes on that. This is an ACS exam, so it is standardized. It's put up by the American Chemical Society. It is pretty much given at almost every college and university that offers general chemistry. How this is going to work, you'll have 70 questions and 110 minutes, so that's under 2 hours. Just under 2 hours, which puts you at roughly 1 minute 34 seconds per question. So it's pretty fast, I would suppose. But some of these questions that you'll see are going to be pretty obvious right away. So thankfully, what they're doing this semester is because they are designing it for online use, is that they give me extra questions. So what I can do is I will put up a practice exam just like it. So what I'll do is it'll have 70 questions, 110 minutes, so you can practice working under those time constraints. And you can also see the types of questions that you'll be given. And then, of course, I'll make the answers to that visible as well. So you can double check everything that you're doing on that. So we're in the process of acquiring the exam right now, so I don't have the stuff yet, but I will. If we take a look at the... I had written in the Discord because I don't remember. The topics for this are going to be... the way that they've set it up, they have a different kind of array of topics that we're going to have. That... let's see, what do we have here? So we're going to have physical properties... and IMFs, intermolecular forces, so stuff we've talked about. We'll have phases and phase changes. So that's going to include, phase change diagrams, things like that. So if we want to go over these, since I know it's been a long time since we've talked about this stuff, we can do stuff like that towards those review days at the end. We can spend a little bit of time on that. Or I can just kind of post the relevant videos for that so you can re-watch them. I'll just make them a little bit more obvious to us. Of course, we'll have kinetics, equilibrium. So that's all sorts. We have Kc, Ka, Kb, Kf, Ksp. All those equilibrium things are fair game here. Acid-base stuff, including buffers. Thermodynamics. That's the delta G stuff, and then electrochemistry. So, we're lucky in that nuclear chemistry, well, I could say unfortunate because nuclear chemistry is easy, but nuclear chemistry is not part of your final exam, so you'll just have homework on it. If I remember correctly, there will be some stuff about transition metals with physical properties, but it's not going to be a huge thing on your final exam either. So these last two chapters are not going to be kind of the focus on your final exam. So it'll be more towards other stuff. So, all right. So, but you'll see on the practice exam once I've put that up for you guys how that'll work. Okay, and you'll see what kind of stuff they'll give you, all of the constants and formulas and stuff that you'll need, so you'll have that there. It will be open book that I can't stop, but consider that you have 1.5 minutes per question. That's not time that you can spend looking around, looking for, searching your book for every question. If it's here and there, you might have time, but you certainly will not have time to do it for every single question. So, just so you know, again, the exam is designed for a median of 50%. That is what it is designed for. So when you see your score, don't panic. Okay, it's designed for a median of 50%, and then scores are going to be adjusted accordingly. So as a standardized exam, that's just how it is standardized. Is that they shoot for 50% in terms of the speed of the exam as well as the kind of array and difficulty of the questions. So it's designed that way. So again, don't be horribly shocked at your score because there will be an adjustment for it. Okay, so that's not something you're going to need to worry about. Okay. Let's see. Anything else I want for that? It'll be conducted on Canvas. It'll be multiple choice. So you'll be able to do that. You'll be able to look at your past questions and go over things at the end. It'll have the little timer in the top. You'll see this again when you do the practice. I definitely suggest you do the practice, by the way. Like, why wouldn't you? I think it would be a good idea to do that. So we'll work on that. All right. Any questions on the final? So again, you'll have 2 days to do it. So somewhere in that, you'll want to book off 110 minutes, maybe a little bit more. Have everything ready to go. So as soon as you do it, we'll do it. If there's technical problems, let me know. We'll deal with it. But I'm hoping things will go pretty smoothly. So, all right. There's no proctoria or anything either. Completely open book. Whatever you want to do, go right ahead. So, all right. But again, 1.5 minutes per question. So keep that in mind. All right. Cool. So if there's no questions on the final, we can, I guess, go ahead and start. Oh, I guess I can talk about the rest of it. So I have your exams to grade. I posted your exam key this morning, so you can take a look at that. I'll be grading those over the coming week or so. And I guess I'll also be grading your homework. we're kind of at the point now in the semester where I am more generous with grading homework because I just want to get it over with. So that's, I guess, thanks for your patience. I will have a little bit of an extra credit survey at the end, just like with last semester. So there's that as well. So I just asked for feedback on the course and on my teaching and all that. And so if you do that, you'll get a little bit of extra credit. And I don't look at that until after the semester anyway. So I just see who's done it, and then I'll give you extra credit. And then after I submit the grades, then I will take a look at the answers there. I also do typically adjust the grade percentages, letter percentages as well. So I always look at how the class is doing, and I say, okay, well, we have this cluster of students here, cluster of students here. That's where I usually make the grade, the letter breaks. So it's not, rigid at, 79% is your B or whatever, but it's gonna be flexible depending on the class. Okay. Cool. So we'll have 2 more homeworks, and we'll have our final exam. That's it. I think there may be another lab similar to those. Have been out there, so some of you may have already done them, but that's all there. And then we'll be done. So we just have a little over 2 weeks left to go. So it'll be bittersweet. So, and okay, cool. Any questions on that sort of thing? And what I'll do is I'll make your homeworks for these 2 next chapters. Yeah, right? It does feel like that. I'll make them do a little bit later than I normally would, just so you can take your time with it. So, because it's not going to be on the exam or whatever, I'll just make it due like later. Okay? Yeah, definitely did go by quickly. So, oh well. That's the way it is. So maybe I'll see a bunch of you next semester as well. There is talk of potentially doing a few labs in person, but I know some of you do come from more distant areas. We'll see what we're going to do with that. That's just kind of something that's been thrown in the air. I've been kind of like, yeah, it'd be cool to do an experiment or 2, but then we have to worry about safety as well as like, oh my goodness, is chloride traveling through the salt bridge? I suppose it depends what the salt bridge is made of. Let me get back to you on that, Kevin. I don't want to think about electrochemistry right now, so I'll post the answer to that in Discord once I've thought about it a little bit. So, but we'll go through that. Yeah, nobody wants to think about electrochem anymore, right? Though unfortunately is on your final, so we'll deal with that. Alrighty. Cool. I presume, yeah, so now I have to, because now it'll be stuck in my head. Okay, here we go. Here's our cell, right? I think that one we had, was it KCl on both sides? Here we have our silver electrode. We have our platinum here that's got the mercury. Oh, silver nitrate. Oh, of course. Wait, really? Silver nitrate? Oh, yes, of course, we need the silver ion stuff. And then we have this is the KCl then on this side. So, so with this particular one, we did see that the mercury was acting as our cathode, and then the silver was the anode, right? Very, very slight difference there with their... yeah, and I hate... Those are my least favorite as well. That's pretty funny. Yeah, kinetics, I just... Okay, so if this is the reduction side of things, that means electrons are going to be moving along this way from the anode to the cathode as they go through, which means we are going to be spitting out silver ions here. All right, into our silver nitrate solution. So as we do that, we're going to be attracting anions. We'll be moving into that solution as well to balance it out, right? And so technically, yes, it would depend what your salt bridge has been soaked in. But you're going to have chloride ions here as... Actually, this one, you're not going to have to worry about chloride ions going through. So, because this one, everything will precipitate immediately as... Oh, shush. Actually, you are releasing chloride ions, yeah, as the mercury goes through. So you will have chloride moving through here. It's a question if it will go all the way across, because it just depends on what's been soaking with your solution for your salt bridge. I may have misread this one, so it may have been the nitrate ion for one of them instead of chloride. And so you're looking at Q being your, for the concentration cell, that'll be kind of like your dilute side over your concentrated side. That's kind of what we're looking for. So if it's silver nitrate, the nitrate ion is what we're probably going to be looking at there. So as well as, so maybe we do have some silver ions. So we'll take a look at that again in more detail once I think about that again. So, but right now let's forget about that. Let's not worry about this. I'll look at that again. I might have just, for whatever reason in my brain, thought about silver chloride being on the other side. I thought there was silver chloride on the other side in the anode. We'll take a look. All right, hold on. Let me get Oz because he's just barking up a storm. No, the trucks are not scared of you barking at them. Okay. Alrighty. So, anyways, I'll look at this again. We'll have a look. But I don't imagine it would change. It would just change the identity of the solution. So, but we'll see. Okay. So, anyways, let's talk about transition metals. And these are going to be coordination complexes as well. We'll learn about all this kind of fun stuff. So, we've talked about pretty much every group now on the periodic table except the transition metals. And they are pesky. Primarily because they will form multiple oxidation states. So, they have a variety to their behavior. Now that we've studied electrochemistry, we can see kind of some reasons that some will spontaneously form certain oxidation states. It just depends kind of on the delta G's about it, which we can tell from the electric potentials that we saw with the galvanic cells. But this is why they're particularly tricky. So they will typically form multiple oxidation states. There's a few exceptions. But notice all of them will form oxidations, or form positive ions, cations, by losing... They will lose their s electrons first. Right, so transition metals typically they have Ns2 and then some d electrons, right? Let me make that a little bit clearer. Whatever they happen to have. There's a few exceptions. For copper, for example, copper is what, 4s1 3d 10, if I remember correctly. Or is it... Where is copper on this thing? Yeah, 10. So, because of that, copper will form a 1+ ion. That's a a little bit special. A lot of these don't typically form 1+, but we're going to see that almost all transition metals. We're going to see silver is also in that same bucket as copper, so it has the just one s electron. All transition metals form. We're going to see that most of them will form +2 ions. And then the rest of them will kind of follow a little pattern here. They typically will go up and then down as we go through. Let me offset that so it's not actually at 0. They typically will form... I need to make this a little bit smaller. All sorts of different ones. So as we look here, as we start with, let's see, scandium, titanium. What's after titanium? Vanadium. Chromium, manganese. I have to redo this chart once I actually write out all the elements. Manganese, iron, cobalt, nickel, copper, zinc. Is that 10 of them? Yes, that looks good. So we're going to see, let's skip scandium for now. But typically these will go up and then down again. We have some special cases. Scandium will actually prefer to form a +3 ion because it's so close to just losing its extra d electron to form a noble gas configuration. So it's happy to lose those 3 electrons rather than just 2. We're going to see zinc, on the other hand, will only lose its s electrons. So scandium will lose all 3. Typically, zinc will only lose 2. Copper is special that it can lose 1 because it forms 4s13d10. But it can form +2 as well. Can form higher. We're going to see that these tend to increase as we move up to a point. Around manganese, we see that kind of +7 oxidation state there. That's kind of around the highest we get. The reason for this, if we look at molecular orbitals, we thought we were done with molecular orbitals. How silly. And metallic bonds. We have, I guess these are not sigma, are they? Are these delta bonds? Yeah, they're delta bonds. So as we go through these, if you were to take 2 manganese, manganese has 5d electrons. It's going to have all this kind of happy... Actually, you know what? This is size that I'm talking about. No, hold on. Get this away for now. We'll hide this. We'll hide that trend for now. With these, we're going to see that the oxidation states tend to increase, and then they start decreasing again because of the d orbitals being more and more filled, right? So we're going to see that as things start pairing off, they become harder to kind of separate there. So as we go up, of course, we're adding d electrons as we go up. So that just means we have the opportunity to remove more, right? We can continue to remove more and more electrons the higher we go. And then at this point, right around halfway, we see that electrons start pairing off. And they are harder to remove at that point. So we see that we see the oxidation states tended to decrease. So you end up getting your highest ones around manganese or so in the middle there. You typically have smaller ones on the end. But remember that, you know, some of these still prefer, like iron prefers +2 and +3, right? But it could go to +6. Why not? That's not unknown. They can go all over the place. So you'll see that a lot of these oxidation states do exist for many of these elements. Some of them just have preferences depending on their electronic structure. So we're going to see that iron typically, which is 4s2 3d6, 1 2 3 4 5 1 2 3 4 5 6. Yeah, it is 2d6. Okay. If we lose the 2d electron or 2s electrons, we get Fe2 plus. If we lose one more, that becomes Fe3 plus. We remember that having half full orbitals was a good thing. So at 3d5, it is happy, but it can lose more if it needs to. So it's kind of, remember that half filled are kind of in between completely filled and empty. Those are the best states you can have in orbital. You can have a completely filled, that's great. Completely empty, that's great. And then half filled is kind of, you're like, if you can't do anything else, that's a good place to be. But it's not as stable as the other two. But that's why iron typically will form those two oxidation states, but it can do others as it loses more d electrons as it goes through. Manganese at 4s2 3d5 typically most often takes 2 plus, 4 plus, and then 7 plus. These are very common states for it. So we have no d electrons left for that. We have 3d5 left, and then for 4 plus we have 3d3. And then we will lose our other electrons. We will lose the other 3 to get rid of them all. And so we just have our noble gas configuration there. And so we can kind of see that these d electrons, they're not valence electrons, right? Because they're not technically in the outermost shell, but they're also not core electrons either, strictly speaking, because they do react. With chemical reactions, we don't get rid of core electrons. That's just not something we do because they're just way too high in energy. But these d electrons are not quite valence and they're not quite core. They're just kind of in between. So sometimes they'll react, sometimes they won't, which is again why we end up with these multiple oxidation states. When we saw that we're just losing valence electrons for something like aluminum, it just loses its 3 valence electrons. It only forms, become more like... Yeah, typically, because they start pairing off, right? And so once they're paired off, they're a bit more stable, and so they're a little bit harder to react, for sure. Yeah. And they're also going to be held tighter to the nucleus, as we're going to see as we get through there with higher effective nuclear charge, that sort of thing happening as well. But we start also feeling anti-bonding, so that we'll get into that stuff in a sec. So, we're going to see that d electrons typically are going to just be in between these things, and they can kind of do what they want to do. And we're going to see that we're going to have all sorts of different things affecting these d electrons. But d electrons also are special. They give rise to color. So we're going to see that the transitions that d electrons tend to go through, the energy levels in d electrons, tend to be in the range of visible light. So many transition metal solutions or complexes are very brightly colored, ranging, pink, green, blue, purple, all over the place. You can have all sorts of different colors as a result, because these d electron transitions are right in the colorful range there. And so we do typically see that most transition metal complexes are colorful. as the electrons are moving around here. Alrighty. We're going to see, however, that atomic size tends to follow something like this, though. A pattern like this as we increase our what's this? Atomic number. There we go. As we go through this. So here we have our scandium and here is our zinc. We tend to have a pattern like this as we go through. That is actually pretty similar for lower periods as well. But we're going to see that, of course, that our effective nuclear charge increases as we go to the right along the periodic table. We have more protons, and so the electrons are pulled closer, resulting in a smaller radius. But if we take a look at now some molecular orbital diagrams, for manganese, we have 5d electrons per manganese. Oops. We see that those all form bonding delta bonds. Those are metallic bonds for us. But as we throw on more electrons, so if we say we now go to, after manganese is iron, if I remember correctly, we start filling anti-bonding orbitals as we go through that. And if we instead make it something like, I don't know, copper, let's not use copper because it has a special configuration. How about we use nickel? We end up with even more. How many did I just add? 4. We end up adding more and more anti-bonding orbitals to this mix, and so the more delta star orbitals we have more repulsion, and therefore we have larger atoms. So after manganese has that perfect 5 and 5. Happily makes bonding delta orbitals. And so as we add more than that, we start filling anti-bonding shells. As we fill anti-bonding shells, things get less stable. They tend to be more repulsive, and they spread out a little bit, making them large again. So that's why we see kind of right here is where we have our manganese in the middle. And the things going to the right tend to be bigger again, as well as to the left. So we have Zia effective being kind of the dominant force here. And then we have the delta star orbitals being filled up on that side that tend to make them bigger again. So we typically have a trend in the transition metal, the D block here, that's comprised of kind of 2 factors. And so in that kind of middle areas where we have our smallest one before they start getting a little bit bigger again. And then, of course, once we get to the p orbital, they just get smaller, smaller, smaller as they go. All right. What's interesting, though, also, is that transition metals in period 6 are almost the same size as the transition metals in the 5th row of the periodic table. And the reason for this, if we take a look at our periodic table, I'm going to do it this way. Let's go all the way down. So here's our 5th row and our 6th row, right? We have yttrium here. Yeah. And then we have lutetium here underneath it. Or is it no, yeah, lutetium. Interestingly enough, these ones have roughly the same size, even though it's a period down. The reason for that is because as we go from period 5 to period 6, we introduce the F block, right? We have 4F kind of chilling over here. And so while normally more shells equals larger atom, we saw that as we go down the periodic table, we increase in size before. But what's special here is that as we go through from period 5 to period 6, in the kind of analogous spots, they tend to have actually the same size as each other, even though they have more shells. And the reason for this is something called the lanthanide contraction. And that's because we have a huge jump in effective nuclear charge as we go across the F block here. So we have a whole bunch of other elements in between that are going to help to make our things smaller. So we know that as we go to the right, they get smaller, right? And so even though we're going down a step, because technically we're much farther to the right, if you were to kind of think of it in that way, they tend to equalize each other. So because of that, since we're filling up the F block, we have 14 extra protons than we would expect. We're going to actually have roughly the same size as each other. So the radius of yttrium is about the same as the radius of lutetium there. So as you go through, they have roughly the same size, but there's still that same trend. So we still see that kind of dip as we go through, as the delta star orbitals tend to fill up. So kind of fun general trends here about this sort of thing. Alrighty. Most transition metals, by the way, are found in rocks. So we typically don't see these as distinct elements. We don't just say, okay, here's random piece of cobalt in nature. We find these in kind of mineral deposits, right? So we don't actually find the metals themselves, but we find them as compounds called ores. So if you want to obtain a bit of a transition metal, you need to first mine the ore from a deposit. You need to kind of concentrate the metal. By whatever means you do that. Then you smelt it. And by that you reduce it to the what's that? The zero oxidation state. So the neutral oxidation state, you'll smelt it there, and then you can kind of do your fun stuff with it. You can react it and do whatever you're doing with it. So that's kind of the process here. So you'll roast your ore to kind of get rid of extra stuff. A lot of these form carbonates or sulfides that you can burn off, thereby concentrating your metal that you're looking for. And then you can smelt it with various additives to reduce it to from its whatever oxidation state it happens to be in to zero, so that you can actually use it as a metal. And the book has a whole bunch of various minerals in there that you might be getting some of these from. For example, let's see. I don't know. That's a funny one. You have something like cobaltite, where you have in this you'd probably have cobalt in +5 oxidation state. Just guessing here. That would be my guess as to what the oxidation state of the cobalt is here. So once you get it, once you've mined your cobaltite, you would throw it in a furnace or something to roast it, so you'd get some of these extra elements away. So for example, or you could treat it with something. So we know that sulfides can react with acid. They can just react with hydrogen gas as well. Depending on the chemical properties you're looking at, maybe you don't want to put acid because you don't want to form side products or something. And then we can kind of smelt it later to get that cobalt from +5 to +0. Once it's +0, it's metallic. It resembles normal metals, silvery and hard and all that fun stuff. And then we can work with it there, so that we can react it with whatever we want to get whatever we want out of it. There's a whole bunch of other ones here. A lot of them we see have these kind of common names. Sometimes we can have... what are the iron ones here? Let me check it out. This is hematite. That's that kind of silvery black one. And this is magnetite here. So you have these kind of common names. Yeah, right? Cinnabar is kind of a reddish brown mineral too. So, I mean, go figure. You have mercury, which is a silvery metal. You have sulfur, which is a yellow powdery solid. You put them together, you get this kind of reddish brown chunk. Galena is, I want to say, my favorite one. It's this really shiny, very nice kind of cubic structure. That is, it's really heavy, of course, because it's super dense because of the lead. It's pretty cool. So all of these sorts of different minerals would include the transition metals. You can see here that with different oxidation states and different kind of arrangement of the atoms, you can end up with different minerals. And so you get all sorts of fun things. There's absolutely no reason to memorize these names. These are, if you're in geology, go ahead, I guess. Maybe that's something they do in geology, but we'll see that these minerals typically have common names that are, I don't know where they come from. I mean, cobaltite, I can guess, but something like galena, like, what's the rationale behind that? Who knows? So we have kind of things going on there. What else do we want to talk about with this? Oh, I guess let's talk about magnetism while we're here. We're going to see that we are going to have all of our kind of magnetic, whatever we think of as magnetic, metals will be transition metals. Typically, we're going to see that iron, cobalt, and nickel are going to be ones that we typically make magnets out of for these reasons. So just so we remember, we talked about diamagnetic and paramagnetic last semester. We saw that the electrons are all paired off and they are repulsed by a magnetic field. B be a magnetic field. And we saw that we had paramagnetic substances as well, where we have electrons that are unpaired, at least one unpaired electron, and those are going to be attracted to a magnetic field if you apply a magnetic field to them. But we're going to see that these are kind of weak things happening here. We're going to see that we have more definitions now. So typically when we think of magnets, for example, in iron magnets, we are looking at what's called ferromagnetism, where not only do we have unpaired electrons, but they are going to, in fact, they're going to be all aligned with each other. And so we know that we have kind of spins, right? And so if we kind of look at all of these put together, if they're all pointing the same direction, oftentimes we just describe magnetic moments as arrows pointing up or down. A ferromagnet will have them all kind of aligned together. And we're going to see that these will be, when these are parallel to a magnetic field, they are very strongly attracted. And if we were to have them perpendicular, they would be repelled, right? I mean, we know how magnets work. You have one side that is, for example, the north side, and then you've got the south side. And so it just depends if you are aligning your magnet with your magnetic field. Either that magnetic field is generated by some other magnet. You can either get it very strongly attracted or very strongly repelled, right? And so we're going to see that this is what happens here. If you apply a magnetic field to a ferromagnet or a ferromagnetic substance, you make a permanent magnet. So once these electron spins are aligned together in a ferromagnetic material, you will end up having them so that they are stuck that way because it's attractive for them to be arranged as such. And so you'll end up having a permanent magnet. We saw that a paramagnetic substance before, like oxygen gas, is attracted to a magnetic field, but as soon as you turn off that magnetic field, it goes off and does its own thing again. The electrons go kind of out of alignment and they just do their own thing as they just kind of go through it. So we're going to see that. However, when you have something like a ferromagnet, you are actually going to make a permanent magnet. The spins are going to be aligned this way. All right, so if we contrast that, a paramagnetic substance will just kind of have, so we see that these spins are all aligned in one direction here. So in this case, in a paramagnetic substance, we're going to have them just kind of like zipping all about as they're just kind of relaxing here. As soon as you take off your magnetic field, they all just kind of go their own direction, and that's enough of it, and it just goes away. But a ferromagnetic substance will keep everything aligned as it goes through. All right. We have another type of classification called an antiferromagnet, which will be the opposite. Where previously saw there's all aligned here. In an antiferromagnet, they're going to be permanently aligned in the opposite direction. So these are, aligned. So they're not all aligned in the same direction. They're aligned in opposite directions. And we're going to see that the magnitude are identical and they cancel each other out as a result. And so these will have absolutely no interaction with a magnet whatsoever because they're going to be both attracted and repelled equally at the same time. So nothing's going to happen with that. And so you're going to have your magnetic spins from the electrons spinning around opposite to each other. And since their magnitudes are identical, they all cancel each other out. So you'll have no no magnetism at all. And just for fun, because we like to have things that sound the same, we have ferrimagnetic substances as well, where these are arranged in opposite directions. But if you see the way I've drawn them, oh my gosh, this is so hard to draw these arrows. We're going to see that these are aligned the opposite, but don't cancel out because the magnitudes are different. And so as a result, this will be still weakly magnetic. So because you have a greater kind of extent, so in this example I've drawn here, we see that the ones pointing up are bigger. So when it's aligned with a magnetic field in that direction, you will experience some attraction. And so you can kind of have these ferrimagnets. They're not nearly as strong as ferromagnets because ferromagnets have everything aligned. But these will have some magnetic properties. All right, so you will get some magnetic stuff happening here. Interesting to note, a couple of lanthanides, neodymium and samarium, are also often combined with iron, nickel, or cobalt to make very strong magnets. So neodymium and samarium are also, they're lanthanides, so they are in the F block there. Oftentimes you'll see these in where you need very strong small magnets. I don't want to call them super magnets, but super magnets. So, for example, in headphones, where you're going to need magnets in headphones. Don't ask me the electronics. I don't know why, but I know they're in headphones. You'll have neodymium-based magnets in there because you can have them be kind of really, really small, and so they're going to be less kind of heavy as you wear them, so they can be very strong. Let me see what the there's a couple of these here. Yeah, here we go. So, for example, apparently alloys like this. What's the iron? When you have alloys like these are going to be super strong magnets that you'll see. But notice again, they do still deal with the ferromagnetic metals here, and the samarium and neodymium can just kind of enhance them, so they become like extra magnetic as you go through it. So it just so happens that now you can have the F electrons playing into these as well, and so you can just make them extra strong. So we have that kind of sort of fun stuff there. Alrighty. Cool. The last thing about magnets that we're going to talk about is that once a magnet is heated sufficiently, you end up randomizing the spins. Just, as things get heated up, they're moving more, rapidly, they're vibrating more. Eventually, you'll reach a point called the Curie temperature, is when a material becomes paramagnetic. So you might have a ferromagnetic material where everything is aligned. You heat it up to a certain temperature. At that point, things just spin all over the place, and you no longer have a ferromagnet. It's not, and so if you want to make it into a permanent magnet, you can. You just have to stick it in a strong magnetic field, and you'll end up getting your magnet out again afterwards. So just this is a characteristic temperature for various materials. You'll see that often we like to keep magnets cold as we do them for various reasons. This is one reason, so that as we are working with magnets, we don't have heat coming off from our whatever work we're doing, causing them to lose their magnetism. So we often do like to have cryomagnets, but there's other reasons to cool magnets too, to make them extra strong. We see that we have electromagnets as well. Electromagnets will have resistance. Resistance means heat. And so if you cool those down, you're going to reduce the resistance that you have. You'll have less heat going on. Again, less chance for things to go awry through this once they reach their Curie temperature. Okay. And then... Oh, I'm sorry. There's. This is only for ferro and ferrimagnetic materials. For antiferromagnets, they have a different temperature called the Nate temperature. Is when your antiferromagnet becomes paramagnetic. Don't need to know that, but there it is for you. So they just have a different name because your antiferromagnetic is not magnetic at all, but paramagnetic stuff is slightly magnetic, right? So it's just going the opposite direction. Ferro and ferri are kind of magnetic, or rather ferro is supermagnetic. It becomes less magnetic at the Curie temperature, but at the Nate temperature, your antiferromagnet, which is not magnetic, becomes slightly magnetic. So it's just kind of going the opposite direction there. So they have a different name for it. Okay. Enough about magnets. And I guess we're out of time too. So tomorrow we will continue on talking about these transition metals. We'll start talking about dative bonds and ligands and coordination chemistry, which is a whole bunch of fun. So we'll get to that tomorrow. Okay. Cool. With that, see you tomorrow.